The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. I once taught with a professor who was lamenting the fact that as the term progresses, attendance at lecture tends to drop off and gets pretty dramatic by the end of the term when you're lecturing and nobody's there. And I asked him what he did about it. And he thought about it and he said, there's only two things that can get students to come to lecture: candy and sex. Now, we've already tried candy, so today we're going to talk about sex. In fact, we're going to use graph theory to address a decades-old debate concerning the relative promiscuity of men versus women. Now, graphs are incredibly useful structures in computer science, and we're going to be studying them for the next 5 or 6 lectures. They come up in all sorts of applications: scheduling, optimization, communications, the design and analysis of algorithms. In fact, next week you're going to see how 2 Stanford graduate students became gazillionaires because they used graph theory in a clever way. But let's talk about sex. The issue that we're going to address today is one of the most talked about and most well-studied questions in all of human sociology. On average, who has more opposite gender partners, men or women? Now, opposite gender is going to be important, and by this I mean one boy and one girl. All right, I'm not making a political statement. It's just that the math is a lot easier that way, as you'll see. Now, I'd like to start by taking a poll here to see what you think about that. So raise your hand if you think men, on average, have more opposite gender partners than women do. Ooh, only a few. You can. Yeah, 1 on 1. Okay, so let's say over the course of their lives, or over the course of 2010, that men in America have more opposite gender partners than women in America, say in 2010. Raise your hand if you think men have more going on. All right, a bunch of you. Raise your hand if you think women have more opposite gender partners. Oh, this is unusual. Maybe even more voted for women, but it's close. Raise your hand if you think it's equal. All right, about the same. Raise your hand if you think there's no way to know, that it's hopeless to really figure it out. All right, nobody goes for that. Yeah, all right, good. All right, well, now in the popular literature, I think the feelings are different than expressed here. Pretty much universally in the literature, it's believed that men have more opposite gender partners than women. And in fact, you can even think about that if you think about literature. You know, the leader of the harem is always a man, and he's got lots of women. You know, in polygamous cultures, it's always the man that has multiple wives, not the reverse. Now, not surprisingly, this issue has been studied scientifically, I'll put in quotes, extensively. In one of the largest studies ever done, researchers from the University of Chicago interviewed 2,500 people at random over several years. They brought them in on many occasions to try to get the answer for the question once and for all. And they wrote this 700-page book called The Social Organization of Sexuality: Sexual Practices in the U.S. Actually, walking around with this book has proved to be a little embarrassing. Last week, my 11-year-old daughter saw it, and she goes, "Dad, why do you have this sex book?" And, I grabbed it back and I said, "That's for the course I'm teaching." I thought I'd gotten away with it, and everything was fine. And then later that day, she texted all of her friends about the new news that, what do you know, her dad teaches sex ed at MIT. Anyway, this study concludes that, on average, men have 74% more opposite gender partners than women. is one of their central claims. And this is in the US. Okay, now, when you think about it, that sounds maybe reasonable. You know, it might be okay. But not according to ABC News. They did a poll of 1,500 people in the country in 2004 and concluded that the average disparity is much greater. In particular, in this study, they said that the average man has 20 partners, I'm assuming over their lifetime, and the average woman has 6. And this gives a disparity of 233%. So ABC News did a smaller survey, says that it's 233% here. Much more than 74%. Now, ABC News claimed this is one of the most scientific studies ever done, and that there was a 2.5% margin of error. Now, we'll actually talk about what that means mathematically later in the term when we do probability and do study polling. Now, of course, I should also mention that ABC News is the one that said Al Gore won the presidential election in 2000, I mean. Now, the study is called American Sex Survey, A Peek Between the Sheets. That doesn't sound so scientific. And it was on TV, on Primetime Live in 2004. The promo for this is really good. It says, a groundbreaking ABC News Primetime Live survey finds a range of eye-popping sexual activities, fantasies, and attitudes in this country, confirming some conventional wisdom, exploding some myths, and venturing where few scientific surveys have gone before. By the end of today, we're going to agree with that last statement. Okay. Now, who do you think's right? University of Chicago? Who votes for 74% as being pretty close? A few of you? I've already sort of slammed these guys. Who votes for ABC News as being more accurate? Yeah, nobody. Who votes for No Way to Tell? I got some votes there. All right. So how do you tackle this problem? You know, in theory, we could do our own 6042 survey. I don't know how much we'd really learn, and for sure I'd get fired. So I don't think we're going to do that. But fortunately, this is the kind of question that can be handled and actually answered by graph theory. Even though it might be more interesting to interview thousands of people and find out what's going on, that's not as efficient as using graphs. So let me start by defining what a graph is. Informally, a graph is just a bunch of dots and lines connecting the dots. It's actually very simple. So here's a graph. These are the nodes, and they're connected with these lines that are called edges. And often the nodes and sometimes the edges are labeled. For example, we might call this x1, x2, x3, x4, x5, x6, and x7. All right, that's an example of a graph. Now, this being a math class, we've got to give a formal definition of a graph. And we'll usually use the formal definition. A graph G is a pair of sets, often called V and E, where V is a set of elements called vertices or nodes, and it has to be non-empty here in this class. And we'll go back and forth between vertices and nodes. Even in the text, we use both words interchangeably. And E is a set of 2-item subsets of V, and they're called edges. So for example, over here in this picture, V is the set of nodes is x1, x2, x3, up to x7. That's the nodes. And E, the set of edges, is pairs, unordered pairs of vertices. So for example, x1, x2 is an edge. And it's the same as the set x2, x1. Doesn't matter the order here. Later in a week or so, we'll talk about directed graphs where the order matters. x1, x3 is also an edge here. And so on. I think we've got, let's see, 1, 2, 3, 4, 5, 6, 7 edges in this graph. And the last one would be x5, x7. Edges are also sometimes written with this notation. x1 line x2 is another notation. And then later when you talk about directed edges, we'll put a little arrowhead on one end of this. Now, the definition of a graph is really pretty simple. Just think of it as dots and lines if you want. But there's often differences in how people define graphs. For example, in this class, we don't allow the empty graph, i.e. the graph with no nodes. So we're going to insist that every graph has to have at least one node in it. And that's just to make the theorems we're going to prove be true. Otherwise, there's some theorems that are false for the special case of the empty graph. But we don't require the graph to have any edges. In fact, it's possible you have a graph with nodes but no edges. For example, this graph, 3-node graph. So here G equals VE, V equals x1, x2, x3, and E is just the empty set. Now for a general graph, when you do have edges, we say that 2 nodes, call them xi and xj, are adjacent if they're connected by an edge, namely if xi, xj is an edge. All right, so for example, x5 is adjacent to x7, but it's not adjacent to x4. There's no edge there. Closely related is the definition of incidence. An edge E, which is xi, xj, is said to be incident to its endpoints, xi and xj. Okay, so for example, if I label that as edges E, E is the edge x1, x2, and it's incident to x1 and incident to x2. Then we can talk about the degree of a node. The number of edges incident to a node is called the degree of the node. So for example, what's the degree of x5 over here? 3. So in this case, the degree of x5 equals 3. the degree of x7 is 1. These guys all have degree 0. There's no edges incident to them. Now, in this class, we're going to look at only simple graphs, at least for a while. A graph is simple if it has no loops or multiple edges. Now, a loop is an edge that only connects up one node. That's a loop, and we don't allow it. A multiple edge is where you've got two edges that are really the same, that connect the same endpoints. Also called a multi-edge. And those we're not going to have in simple graphs. We don't allow this. We don't allow that. Any questions so far about what a graph is? Okay. So, all right, how are we going to use a graph to model the problem of opposite gender partners? That's the question we're after. So, any thoughts about what the nodes of the graph are going to represent? What is it? People. Yeah, so we're going to have people. And in fact, there's two kinds of people here. There's men and women. All right, and we got nodes here for the men. And in fact, in America, there's a lot of nodes here. All right, and so this might be, oh, I don't know, say that's Tom Cruise and Nicole Kidman. Now, what's the edge going to represent? Partners. All right, they were opposite gender partners. And there's actually more edges probably here. You know, we could have Penelope here and Katie here. And, well, probably lots more. I probably don't even know them all. And Ben's over here with Nicole. And Nicole got Jude and Keith. There's actually a website you can go to get a lot of these things here. And Katie went with Josh. It's called who'sdatedwho.com, and you get a big graph. You can start filling in the edges. I don't know how reliable it is. Now, it's really critical that we're only looking at edges from here to here. All right, so if there's an edge between Tom and Ben, I don't want to know about it. All right, so just opposite gender partners. Okay, now in the USA, the number of nodes here is about 300 million. All right, about 300 million people. And the number of men nodes, male nodes, call these VM, and this is VW. By the way, I'm using cardinality notation. When I put bars around a set, that is denoting how many are in the set. In the US, there's about 147.6 men out of the 300. And the number of women, got a W here, is about 152.4 million. So there's a little bit more nodes on this side of the graph than that side in the US. What about the edges? Any idea of how many edges there are here? We don't know. I sure as heck don't know, how many edges there are. So that we don't know. The cardinality of the edge set we don't know. And we're not likely to figure out. I don't even think these surveys really can estimate that. But what we are trying to figure out is the ratio of the average degree of the men to the average degree of the women. Because the number of opposite gender partners you have is your degree here. And you're looking for the average guy degree compared to the average female degree here. That's what we're after. All right, so let's define that quantity. Let's let A sub m equal the average number of opposite gender partners for men. And we can let AW be the same thing for women. All right, now we're trying to figure out, to answer this question, what is AM, the average guy degree, over the average woman degree? And in particular, the University of Chicago says, they say it's 1.74, that the average guy has 74% more opposite gender partners than the average woman. ABC News says it's 3.33, that it's 233% more for the men than the women. Now we're going to figure this out, what this ratio is. All right, just use a little bit of math here and a little bit of graph theory. So let's write a formula for AM. Well, we're trying to figure out the average degree over here. Well, that's pretty simple. We just add up all the degrees and divide by the number of nodes. And that'll give us the average degree. So the average degree is the sum of the degrees over all men, x in the set of men, of the degree of x, divided by the number of men. All right, can somebody give me a simpler expression for this? It doesn't have that nasty sum in it. E, cardinality of E. I'm adding all the degrees here. Well, that's just another way of counting all the edges. Because every edge shows up once and only once in a degree count here. And this is where we use the fact we have opposite gender partners. Right? Because if I had some edges over here, they wouldn't get counted in the sum of the degrees here. All right? So this is just the cardinality of the number of edges divided by the number of men. Any questions about that? Because this is an important statement about graphs in general. When I have a graph like this, which is called a bipartite graph, we'll talk about more a little bit, but where the edges go from the left to the right, if I sum the degrees on the left, I'm just counting the number of edges. All right. Let's figure out a formula for the average number of partners for the women. Well, that's simple. That's just sum x over the women, the degree of x, divided by the number of women. Let me rewrite that so it's clearer. What's a simpler expression for this? Yeah, this sum, adding the degrees of the women, is just the number of edges, right? So that is cardinality of edges divided by the number of women. All right. Well, now we can solve for our formula, average over men over average of the women. That's E over Vm divided by E over Vw. Wow, this is nice. I don't know what the number of edges is, but it just canceled out. And this is just the number of women divided by the number of men. And in fact, we know that that's this number divided by that number, which is about 1.0325. So we just proved that on average, a man has 3% or 3.25% more opposite gender partners than women. No need to do the interviews or spend years doing it. That is the answer. And it has nothing to do with the promiscuity of men or women. Nothing at all. All right? So the Chicago study is way off, and the ABC News study is completely nuts. You know, it just can't be right. This is a proof. All right, now, what happened here? Well, what's going on? What's the reason for why this is true? Yeah?
Well, if a male has a female partner, then a female has a male partner.
Yeah.
And you're not looking at, like, how many males are going to one female. Like, the promiscuity isn't even, like, a part of the question.
That's right. You're just, you know, it takes two to tango, right? Every time you got a guy, you got a woman. And you have the number of relationships going. The average for the men is that number divided by the men. Average for the women is that same number divided by the women. And so if there's more women, they're going to have less partners on average. Has to be. So it really was a stupid question. It's very, very simple to answer. Now, as it turns out, there are endless studies like this in the literature. In fact, a few years ago, the Boston Globe ran an explosive story about the study habits of students on Boston area campuses. And their survey showed that, on average, minority students tended to study with non-minority students more than the other way around. All right? And they went on great length consulting the experts as to why this might be true. Why is it that minority students study with non-minority students more than the other way around? Now, can anyone tell me why it is certainly true and not surprising why that's the case? Because they're a minority. There's fewer minorities than non-minorities. End of story. We don't need this sociology PhD from down the street to explain it to us. All right. We're going to see a lot of other bogus studies later. This is not unusual, especially when we get to probability. Just every day there's a new one in probability. Any questions about this before we leave? Unfortunately, that's most all we'll say about sex today. Okay. Now, in this example, we used an edge in the graph to denote some kind of affinity, you know, between two nodes. The two nodes liked each other in some sense if they were connected by an edge, or they had a relationship of some kind. There's lots of examples in computer science where you use an edge to denote just the opposite, that the two nodes can't be near each other or don't like each other. For example, consider the problem of scheduling final exams at MIT. And they do this after they find out all of your schedules. And they try to schedule the exams so that you don't have to take two at once, or there's as little of that as possible. For example, let's do an example here. Say we look at these 5 classes. Take 6041. And this may not be totally accurate, but roughly. So I've got 5 MIT classes, and I'm going to put an edge between pairs of classes that have overlapping student enrollment. So in this case, for example, we've assumed in drawing this graph that you can't have our exam the same time as 6002, on the assumption there's students in both classes. But you could have our exam the same time as 6034, because there's not an overlapping student or student in both classes. So the exams could be scheduled at the same time. So we've used a graph to represent which courses can't have their exam at the same time. Now let's also suppose we have a set of slots for the exam. And say they're all on a Wednesday. And the first slot is Wednesday from 5 to 7. And the next one is 7 to 9. And then the next one is 9 to 11. And then 11 to 1 in the morning. And then 1 to 3. Getting pretty late. And your job is to figure out how not to have to use these later exam slots. You'd like to use as few as possible so you're not, going too late at night or come before the holidays so you're not having exams on Christmas and New Year's, for example. So the goal is to assign slots to the nodes. Put every node in a slot so you don't have nodes hooked by an edge getting the same slot. Now, this is an example of what's called a graph coloring problem. So let's define that. Given a graph G and K colors, assign a color to each node so that adjacent nodes get different colors. All right, and then the minimum number of colors you need is called the chromatic number of the graph. So the minimum value of K for which such a coloring exists is the chromatic number of the graph. And it's denoted by the symbol chi of G. All right? Because usually you want to use a small number of colors. Now, what does a color represent when we're dealing with this problem? What's the meaning of a color? A time slot. Okay? So let's call this time slot C1, C2, C3, C4, C5. So there's 5 possible colors. Now, of course, we could color this graph with 5 colors. Every node could just get its own color. But then somebody's taken their exam, from 1 to 3 a.m., and, that's a bit of a pain. Let's see if we can do less than 5. Let's say I give this color 1. And let's give this one color 1. That's OK, because they're not connected. I can't give this one color 1, so I give it color 2, say. Now this one I can't give color 1 because this guy got it. He can't get color 2 because that guy got it, so I give it color 3. And, well, I can't do 1, 2, or 3 here, so I got to go to color 4. All right, so 6042 will get the 11 p.m. to 1 a.m. slot. Not so good. Can we do any better? Can we get away with 3 colors? Some say yes, some say no. How many people think you can do 3 colors on this graph? A bunch. How many think you can't do any better? All right, the vote is mostly for 3. Well, let's see. Any ideas? Anybody see how to do 3? Yeah?
Sign C4 to 6034.
Sign C4 to 6034.
Or C1 to 6042.
I can't do C1 to 6042. It crashes, but can I do, yeah?
Put C1 at 6003.
C1 and 6003.
And get rid of C1 and 6034.
Get rid of,
Just C2.
make this a C2. Oh, yeah. All right, these got C1, they're not adjacent. These got C2, they're not adjacent. This can now get C3. So we can have our exam from 9 to 11, which is better. All right, can anybody do it in 2 colors? All right. Can anybody offer a reason why 2 colors may not be possible? Yeah?
Because let's say you could do it with 2 colors.
Yeah?
6041 and 6002 have to be different colors.
Yes.
You'd say C1 and 2. 6042 can't be C1 and it can't be C2.
Yeah. Good. So you can't do 2 colors because these 3 guys would violate that. You got a triangle here. Each one of these guys has to be different than the other 2. So 2 colors can't work. You got to have at least 3 in this case. So 3 is optimal. We have just shown that for this graph, the chromatic number is 3. All right. Now, in general, doing what we just did is very hard. No one knows a fast algorithm for determining the chromatic number. In fact, it's a weird kind of problem because it's easy enough to check that a coloring is okay. If somebody put a coloring on the board, you can check, oh, that works really simply. You just check every edge and make sure the colors are different. But figuring it out, as best we know, you got to try an exponential number of possibilities. So if I had 100 nodes here, my running time of the algorithm to check all the possibilities would be exponential in 100. Yeah?
The highest degree of each node or nodes?
No, but it's no worse than something like that, as we'll see in a few minutes. That's a great observation, and we're going to come back to that in a few minutes. But it's not just that. Okay? Now, in fact, even figuring out for an arbitrary graph if 3 colors can be done, called the 3-coloring problem, that's really hard. No one knows how to solve that in less than exponential time. In fact, it's called one of these NP-complete problems is what it's called. How many people here don't know about NP-completeness? Is everybody? All right, so a lot of you haven't seen NP-completeness. Okay, so there is a class of thousands of problems. In fact, there's books that list these 1,000 problems that are all NP-complete. Somebody's proved they belong in the class. And what that means is that if somebody gave you a solution, like a coloring here, it's easy to check really quickly if it's valid. But figuring it out is really hard, and if you figured out how to solve one of those thousands of problems, like suddenly you figured out how to tell if any graph could work with 3 colors, you would solve automatically all other thousands in the book. So it's this book of problems you will constantly run into in your career in computer science. And it's bad when you run into one because there's no good algorithm to solve it known. But if you just solved one of them, the other thousands would suddenly be solvable quickly. Even better, you win $1 million prize, one of these Millennium Prizes we talked about in the first lecture. Even if you show you can't find a fast algorithm for one of them, that means that none of them have fast algorithms, and you also get $1 million. So this is the central problem in computer science, in theory of computing, is whether or not you can solve these NP-complete problems. Now, actually, lots of people have claimed to do it, and in fact, there was a lot of buzz in the community about a month ago when actually a reputable researcher at HP Labs said he'd done it. He'd proved that you can't solve NP-complete problems. And he got people going for probably at least a week until they discovered a fatal flaw. And the proof was actually bogus. So no one still knows if you can solve these NP-complete problems quickly. Now, the problem is, in practice, you run into these things all the time, like MIT really does have to schedule the exams. So you got to do something. You can't just go say, hey, it's NP-complete, so no exams this year, or whatever. That's not going to fly. You got to do something. So now this is a problem. Many of you, when you go into careers, are going to be faced with this. You got to do something. Any thoughts about an algorithm for coloring graphs that might use a small number of colors. It doesn't have to always work, or you're going to win a lot of money if it does, but a simple algorithm, you can't take e to the 100 steps. You got to be linear, probably, or quadratic time. That could get you a small number of colors. Any thoughts about what you'd do? Yeah?
Number of degrees on the node.
The number, what about it?
Like the highest degree in that node for 6442 is degree 3.
Yeah?
So you can use that.
Good. All right, but so what do I do with that info? So I found a node with high degree. There's 3 of them that have degree 3 here. What do I do with them?
Pick a different color.
Pick a different color. That means I've colored some of the others. If I pick a different color, do I start with them or do I finish with the high degree nodes? Because you got to assign the colors to them. And high degree is important to be thinking about. We're going to prove a theorem in just a minute about related to degree and coloring. Start with them and do what with it? Color it?
Yeah, and then assign the ones that aren't connected, if hopefully you can put the same slots.
Okay, so I could, here's a degree 3 node. I could start with color 1 for that. And then what do I do next? I pick, its neighbors have to get different colors, I guess. You'd start coloring the neighbors.
Well, I guess I would, my first instinct would be to color all the ones with the most degrees first.
Okay. And what color would you use for them? Different ones if they're connected, or if they're not connected, you'd still use different ones?
Only if they're connected.
Only if they're connected, use different ones. And so if they're not connected, you use the same colors? Yeah? All right, so this is actually, you're getting close to it now. It actually works pretty well. The underlying principle you're sort of thinking about here is you've got some notion of the order in which you're going to process your graph. And you're going to start with the high degree nodes in your case. And as you go along, you're going to start coloring the nodes. And you're going to make sure you color them legally. And it sounds like you're going to color them with a low color, all right, as you go along. And that is probably the most basic graph coloring approach. And you could almost say is a generic approach. So let's define that and then prove some facts about it. Most of the graph coloring algorithms in practice are based on this approach. And we're going to call it the basic graph coloring algorithm. And for a graph G with vertices V and edges E. So the first step is going to be to order the nodes from 1 to n. Now, in your case, you were suggesting an ordering where I have the high degree nodes first. All right? But for now, we're not going to specify that. We're going to make it any ordering you want. And then we're going to have a notion of an order on the colors as well. And I don't know how many colors, but they're going to be numbered 1, 2, and so forth. And then we're going to process the nodes one at a time.